Come on, dogs. Go. Go. Call the dogs, Jackie, please.
Come on, get out, get in here.
Start my video. First one, you can stay, man. Please do. Alright. Shut this real quiet. Well, I'm going to attempt to solve the world's greatest puzzle. And here's how I'm going to do it. I'm going to think a whole lot about it. Skip college so I don't have to follow any certain. I choose my own things to study. So here we go. I ain't planning to be right about everything. It's a kind of freestyle. But we're going to try our damnedest. And we ain't going to come to any roadblocks. We ain't going to just come to the notion that it can't be solved. It can be solved. There's no doubt about it. Pretty easily, probably. Okay, fundamental forces. That's where we're going to start. But we're going to call them something totally different. Let's see, we got strong. Uh-oh. Yeah, shit. And my marker's screwed up. Cool. I got one. No. Yeah. Right, see. Strong. Weak. Electromagnetic. Mercadianic. And of course, gravity, but gravity ain't one in the standard model. Of course, it only fits in certain parts. Well, due to these, we're going to also add dark matter, dark energy. Okay, these are going to be our key say characteristics, dynamics, dynamics of nature or some shit. I don't know. Let's call it let's just call it. Let's call it the 1, 2, 3, 4, 5, the 6. The 6 characteristics. How am I spelling terrible? 6 characteristics of nature. Okay, we're going to use these 6 characteristics to resolve the issue here. Inflation is the problem. I mean, but it, of course, it took care of a few other problems. Solved a few other things. But we accept nothing on the speed of light except that. So and we was on the surface of say a volleyball that was expanding, we should be able to see a certain picture of the expansion. I mean, it would be set a certain way, and we don't see that way. Nature ain't that way, so inflation will take care of that. And there's two other problems, but we ain't gonna go into them right now. What we are gonna do, for a long time, they thought gravity would connect to electromagnetic. They was trying to match that all together. What we're gonna probably see though is, if we get close to solving this thing, I think all of them will connect, pretty much. And it'll be like a two-part universe. I think there's a name for that. Nah, I don't know. But some kind of name like two suns in a solar system would be, but only two-part. I think it's by something. Not important right now. Okay, where we're going to start is the strong force. Now, the strong force be extremely strong. If we say likes oppose, opposites attract, then we say that two protons, it's kind of hard to keep them together in one little spot. So we got force carriers, of course, for the math. I mean, we got to name units and have different breakdowns. And the math works, so, we call them gluons, of course. Good name. I like the name. But anyways, where's the problem with that? I think, in my eyes, that hydrogen, if that's the case, hydrogen, I think would be the most stable. Now, we're able to fuse hydrogen. I mean, we're able to put more protons together. And that doesn't make sense. Iron, somewhere around in the middle we have iron. And iron seems to be the most stable nucleus. So let's start with iron. That's the most comfortable stability. That right there is, that nucleus is the right amount of baryonic matter. And of course that's where stars, they kind of only fuse iron with our understanding right now. So it's the most comfortable. Now with this, we take this, now it can be permanently magnetized. Also, one lighter and one heavier. So it can be permanently magnetized. So we got the electromagnetic field kind of in balance. Electromagnetic field is in balance with the strong force there. And the weak force. If we got the strong force holding it together, then we got the weak force kind of breaking it apart. So right in the middle, we have iron, and then manganese and cobalt. I forget which one's heavier and which one's lighter, but I'm not pronouncing manganese exactly right. But I believe iron's 56 maybe. So maybe at 55, I'm not quite certain. And 57 can be permanently magnetized. So, I'll tell you one thing. I'm 50 years old and been trying to solve this forever, so without any reason other than wanting to understand it. So permanently magnetized, these three metals. And blah, blah, blah. Anyways, so what is magnetism? It's kind of wow. First time I remember in science class in like 7th or 8th grade, we took the powdered iron or whatever it was, dust, and put a piece of paper over a bar magnet. It was pretty cool, and then just to see them push each other apart, and it's just, it's invisible. It's like there's a force there. What is this force? It can be in space, it can be anywhere. Anywhere there's an electric current, there's a magnetic field. And if you run a conductive wire through a magnetic field, you're going to get electric current. Everything's electric pretty much. If I was a nucleus, this whole city, Charleston, West Virginia, by the way, my name's Mark Christman. The whole city of Charleston, West Virginia would be like an electron cloud. So that's very important too. Notice the size difference there. So what it is, we got a rigid, very rigid, positive nucleus, and a very, very, very soft, like formable electron cloud. And that's a big difference now. So notice the volume difference. Now, this is the key part, one of the key parts. Volume is going to be a charge per volume. Now, same amount of charge, basically, but we'll get to that. That's not exactly true either. So, but per same. I'm making a video, Jackie. I told you that now. Start my video. So, so charge per volume. Just remember that. Now, we're going to call it baryonic matter because, well, we've seen something way back in the day that it was gaining, the nucleuses were gaining mass quicker than it was pulling a negative field. So we must be the nucleus. Neutrons. What's a neutron? Electron. And a proton. But when we measure the decay, there's two different ways to do that, at least two different ways. One reads 15 minutes and some odd seconds, and another way is a few seconds off, 15 seconds off, depending on which method we use. Now, that's a big deal in science, so a few seconds is like millions of units. But anyways, what we fail to realize that, well, see how big this electron cloud is. Well, it's pulling it. We can't pull it all in. So it ain't so much that we got neutrons in the nucleus. We can't. The more and more heavier the nucleus gets, it becomes more and more of a positive ion. We can't pull the field in. The field, we can only pull in so much. So, because it's spread out. It's spread out compared to positive particles. Now, Planck, he was half right. You see, he said he was using field theory and studying black body radiation. And, well, it was going to infinities. None of the calculations were correct. So he went with units, quanta, and it started making sense. But only half of it's quanta, the other half's the field. So, and of course, the quanta, this particle is shaping the field, which creates a lattice in the field. Anyways, so basically, if we have a two-part universe, let's compare it to a checkerboard, 3D checkerboard. If one shatters and becomes particles, the other has to expand at an equal and opposite rate and become a field. Well, see, this is the field. It's expanding. This is particle. It's losing volume. If the Earth was a black hole, I think it would fit the Schwarzschild radius, I believe it is. It'd be about 3/4 of an inch, 18 millimeters maybe in diameter, if I'm correct. Don't quote me on that, but it's awful small. So you can see that to squeeze the Earth into something that small, well, it seems like volume is it's losing volume. The baryonic matter is losing volume as the field escapes from in between it. Now, the field we're going to refer to as dark energy. Something's expanding out there. We see the shift. Doppler, he was against the expansion of space, but nonetheless, he was studying at the time, so we coined him the term the Doppler effect. But so something's expanding there. Something's causing that. So we got an expansion going on. And in the same way, this field is real big compared to this. Well, the expansion part has a certain energy. If we reverse that all the way back, like we look at a star blowing up, we know when it blows up, how strong it is, so we can measure, we know how far away it is, So then we measure the redshift, and the further it is away from us, the faster it's moving from us. If we take that all and reverse it, all the math, boom, to a big bang, it almost works out, but not quite. So I think we'd be better off taking that instead of a single point, sorry churches, we take it off to infinity to many points of a certain volume that's negative is equal to positive, that's our checkerboard. So we're gonna reverse it to not a single point, but to a single graph, a single checkerboard. So we will do that. And then this expansion, this one turns into a field, the other turns into a particle, is gonna look much like, almost exactly like space looks today. So now, we got one expanded, and that's called, that's a field, that's gonna be the weak energy. I mean, not weak energy, but the dark energy. The expansion is the dark energy. Okay, now the weak force is, it's decaying. Uranium's decaying to lead. So we're gonna say this is the comfortable spot right now in our universe. At this point, iron 56 is the measurement of where we are at right now. That's where we want to be. So that's the strong force and the weak force balanced out at iron right now. Now, as far as gravity, well, what the hell is gravity? Do you think if gravity was a pulling force, well, we know gravity definitely is there. But what is gravity? Is it a result of some other forces? Is it what is it? If it was a pulling force, you know that it would have collapsed long time ago. We would have done collapse long time ago. Now, if we watch something go down our drain, is that a pulling force? No, that's a pushing force too. Also, atmospheric pressure is pushing the water down the drain. Well, this dark energy is expanding. This field's expanding, it's leaving from in between the matter as matter fuses. Look around, all the stars. Matter's coming together, fusing, it's getting heavier. You know, if we look at our weights that we stored a long time ago, they're lighter now. We say, oh, it's decaying, whatnot. No, just the periodic tables, it's rising. You know, we started off with real light, when that checkerboard, something happened somewhere, we started off with wee little particles. The most balanced was way lighter than iron. Well, it's getting heavier, heavier, and heavier. Some parts of the universe, I'm sure, iron is way up. The most stablest is way up high. That's where we get our heavier elements, of course. So, nothing is exactly going to be the same everywhere. Just a little bit faster. Perhaps closer into the middle of galaxies and stuff like that, where you're going to see the heavier, stable point. Now, so if we got this expansion pushing, so say we got the sun right here in the earth, we got dark energy. So we got dark energy coming in from every fucking direction, from millions of billions, 14 billion, at least 14 billion light years away. Well, where are we getting all that at least from? Well, the sun's blocking a lot of that. So we're getting pressure all the way around and a little less from here. So what's that going to do? That's going to keep us revolving around the sun, like the moon and everything. So, and it's also going to, as this gets thinner, as this field stretches and stretches, well, that's the weak force. If that field was strong at some point, the weak force would rise. Now, if the field is thinning out, the weak force, it lowers. Now, let's see. So, neutrons? No. We take a chunk off of a nucleus, and it rearranges the field. The fields all around it are going to rearrange to accommodate the new situation here. So let's see. As it gets heavier and heavier, well, the field, it only pulls so much in. So not neutrons, no, the field is weaker. So everything's a positive ion pretty much, even though there's an equal amount of negative in the universe as positive, the volume difference is responsible for all the characteristics, everything we see, the sophisticated, complex dynamics of the universe makes this all possible from two elements, for not having a better name, two-part universe is able, because of this, because of the charge per volume. One's rigid, one's flexible. And so this is, let's see, how do we define this furthermore? So, dark energy and dark matter. Well, dark matter, when we're missing 70% of the matter it would take to keep the stars on the outside edges of the spiral galaxies from, they're going fast enough, they should be flung out, there ain't enough matter in the galaxy to hold them in. Well, what we doing, 40, 50 years into the search of, well, we need to redefine gravity instead of looking for dark. So we'll cancel out dark matter. Dark energy is going to be the reason why we are well grounded in this world. And the reason, and the shape, pretty much the shape of the whole damn universe is pretty much because of that. And opposites don't attract. Likes, well, right here, we're most comfortable with right there. So, you never get heavier and heavier as space expands out from all the baryonic matter. Now, when that happens at the end, well, it'd be like that checkerboard at the beginning, but a balanced checkerboard. That checkerboard was totally balanced, and negative wouldn't affect positive, and it would be nothingness. So infinity would be nothingness pretty much, until something happens where something moves a little bit, something shrinks, something boom, and just boom, and we got Earth. Now there should be nothing in the universe. There should be nothing existing, but it's inevitable, and it's obvious that I mean, that everything exists. So was there a beginning? Now, beginning, we don't have to start from zero. See, if we want to start, we don't have to start from zero. But what we do have to have is that it's got to equal zero. So for every positive unit of existence of any type, say positive, let's say positive infinity. And what we gotta have? We gotta have an equal amount of negative infinity. So we can start anywhere we want to, as long as the result is zero. So we can start from infinity, we can start halfway from infinity to zero. What the hell is that? I don't even know how to figure that out. But infinity would be like a checkerboard, like just across the whole universe. Now, did it start in one spot where it shattered into particles and one had, well, the other one had to be a field, expand, did it start in one spot and just spread all over and spread, sporadically, or so we was never at zero. It's always been. And could it go to zero? Absolutely could. Could it maybe go close to it and spring back out? Well, that's absolutely a possibility too. I've never figured that out yet. I'm sure people out there can will. We don't know. But there's one interesting fact, although I'm not superstitious, I'm all about science. Going to zero, from infinity to zero, kind of has a turn off from, a religious viewpoint, which I'm not a religious man, but I do believe in God 100%. Man, a creator, perhaps not the one in your Bible, but definitely 100% believe in the creator. So, when we die here, we die, we're no longer in this reality. So, if there's an opposite, maybe there is a heaven that's going from zero to infinity. And since we're not here, maybe we cross over to there. Now, that's just just a little fun thing to kind of make up for the infinity to zero thing. It's scary, but that's basically it. So gravity, the strong force, the weak force, electromagnetic force, it all works together as a two-part universe that is very simple. And I'll, I'm not sure this is right. It looks right to me. I'm just coming to this conclusion. I ain't been able to, I mean, see, I used to just switch this around, switch that around, and try to make this fit and that fit. And, well, one day I couldn't see anything not fitting, but, it's my theory, so my model, so perhaps I'm not seeing something, but I'm not going for any reason other than to satisfy my own curiosity. So I would hope to think that I ain't blinded by biases to my own work, but you never know. I mean, that is a possibility. But I'll be going over each and every one of these things, little by little, trying to solve this puzzle. And I hope you enjoyed my video. There'll be plenty more to come. Feel free to comment.